Okay. Okay, you guys. You have a handout. I know all the limit laws are there. What is a limit? Okay, Lizzie says it's the behavior of a function as the x gets close to a certain point. Mrs. Johnson and I were having lunch together yesterday, and we were talking about limits and how her students are having troubles with them. And so she said, well, this is what I tell them. You're heading to downtown. You don't really care which direction you're going from to get to downtown, because no matter which direction you come from, downtown is there and you can see it, right? So you know where you're going towards. You always know where you're going towards. It doesn't matter which way. But once you get downtown, do you care what happens with that view? Not really. It's now you're downtown. So a limit is like you're looking forward to where that function is going. It's actually the y value. It's the y coordinate. I didn't leave myself any space here, did I? This is where I got smarter. Okay. As x gets near some value, now we don't care what happens at C. Then what is the y coordinate getting near? Okay, well, guys, pay attention. I'm not going to talk for a long time. A limit is the y value, what it's getting close to, getting near. And I know that some of you get bothered, especially when you are looking at a function like this. Does the limit exist here? Yes. And if I put another point there, does the limit still exist? Yes. Okay, because I don't really care what happens at C. At C, I get 0 over 0. It would be nice to have this dot in the right place, but we'll deal with that in section 2.4. So on Monday, you're going to have a work day, and I do have a reserve teacher who does know calculus, so she can help you. We're going to give you a handout on this main limit law. Oh, what are the conditions for a limit to exist? The limit as x approaches C from the left of f of x must equal the limit as x approaches C from the right. In last year's exam, they made you write that out. I don't know which problem it was. Maybe I'll pull it up for Monday and let you look at that question again. You had to say that. I didn't grade that one. But I know you had to say that because I looked at the scoring rubrics. It was on the A, B, and BC test. You are going to get 2 scores. You're going to get another A-B score, which should be going up. I hope. Usually it does. And I would say 85% of the students who took the BC exam last year got 5s on the AB subscore. And our average on the BC was a 4 out of 5. It's kind of interesting. Okay, so. Okay. No. Oh, yes, they're done. They're not in, but they're done. Okay. Not right now. Marshall. Yes. Okay, when we do the limit laws, you can't use these limit laws if the limit doesn't exist. So the limit from the left has to equal the limit from the right. And that's how you're going to show you have limits. But you can't distribute a limit over something that doesn't exist. Let me give you a quick example. What if I wanted the limit of 1 over x minus 1 over x as x goes to 0? I wouldn't want to distribute that, because what is that the limit of? It's 0. So the answer is 0. Can you distribute it and say it's the limit as x approaches 0 of 1 over x minus the limit as x approaches 0 of 1 over x? No, because this is infinity minus infinity, and I don't know what that is. And you might be able to argue that they're the same. because we know that up here. But you really cannot apply that main limit theorem unless each individual limit exists. So then, if that doesn't work, then you have to go back to looking at the limit from the left and looking at the limit from the right of whatever you have. I'll bring in the worksheet on Monday. I'll give that to you so you can see that. It's going to happen. So you know all these main limit laws. You know that you can distribute them over multiplication, division. And you know, of course, that you can pull this constant out, right? Remember that with limits, Duncan? Okay, so you know you can do that. And the power rule, you can just take the limit, find the limit of f of x and raise it to that power. The composite limit theorem is not in this section. It doesn't look like. Okay. These limit laws can only be used when each limit exists. This is different. We talked about it last year. I said last year, you don't have to worry about it. We'll worry about that in BC. So I'm going to guarantee you, you're going to have some problems like we'll force you to not use the main limit theorem. And look at the left and right on your test for this chapter. You just have to find another way to find your limit. Okay? Remember one-sided limits? Good. Thank you for saying that. All you're looking at it is the limit from one side. So x approaches c from the right of f of x. This is a right-hand limit. And we were just playing with the Inspire CAS calculator in the last class, and I said, I wonder if it'll do one-sided limits, and yes, it does. So if you take the greatest integer function and you look at just from the right or just from the left, you can actually put the little plus or minus into that calculator. So it knows to look from the left, knows to look from the right, and you can actually calculate it out, which was really actually very cool. So that's the right. If I want the left, it's the limit as x approaches c from the left. Now, almost always, but not always, but almost always you can find these. And I just substitute. So if it's a one-sided limit, they're actually easier. We just substitute. It's the main limit theorem that allows me to do this substitution, by the way. Okay? Do you remember the right and left? You just have to look at it from both sides. It's like coming into Minneapolis from this side or coming into Minneapolis from St. Paul. Same type of thing. You're going to get there. They exist. Now, there's a theorem, and we talked about this last year. Do you guys remember what a polynomial is? Probably not. Here's a polynomial. It looks like this, which is really complicated. So to make it simpler, it looks like ax to the n. You could add them up with other terms, where n is not even an integer, it's a whole number. So you have no fractions, no negatives, no decimals. Okay? It's a whole number. If you have a polynomial, the limit exists everywhere. We like that model with polynomials because those are nice. They behave nicely. They're all going to look like this. They're going to be continuous. The limits are going to exist, no problem. Now, a rational function, you know what a rational function is? That's this guy right there. It has to do with ratios. You see the word ratio and rational. And what's an easy word for ratio? Fraction. And you see the word ratio in the word fraction. At least I do. R-A-T-I-O. Don't think that's by accident. I think the derivation of the word probably is connected. So, yeah, I don't know. You'd have to look it up. Now, so these are rational functions. They're fractions. And these are always going to have limits existing, provided that f and g are polynomials. Exponentials might work too, but this is only for this. Okay, and the thing is g of x can't be 0. So you'll have to exclude those points where it's 0. You already know all this, right? Yeah. Okay, Matt? Elliot? So now we have a theorem we didn't do last year. And this is called the squeeze theorem. Oh, wait, let's first do this. What about the limit as x approaches 0 for the absolute value? The only ones where we know limits exist all the time and not having to check both sides are polynomials and rational functions. What about the absolute value? What would you have to do to show that? You'd have to take the limit as x approaches 0 from the left of the absolute value of x. You have to find the limit as x approaches 0 from the right of the absolute value of x. So you actually have to put some values in to see what happens. Or we could simplify it because I know what absolute value of x is. Let me graph it. Here's the absolute value function. That one's tricky. It's a piecewise function. Somebody said, I don't want to write up the pieces. Well, what are the pieces? Yeah, so you guys remember this. Excellent. It's x, that's the right side here, if x is greater than or equal to 0. And if I take the other side, it's minus x. So the mathematicians got tired of writing the piecewise function. I don't know who would take credit for it. I have no idea what the history on it. But somebody said, I'm going to invent something to represent that. And they use those little bars. And they also probably recognize they're always positive. But I don't think they said that the x's go to jail and come out positive like I do. But who knows? That's all you have to do. So when I do this one, this is really the limit as x approaches 0. If I'm coming in from the left, I don't need absolute value there. I can replace it with minus x. Now substitute it in because it's a polynomial. What's this value? 0. How about the right side? Can I rewrite it without that absolute value symbol? Sure, I can do that. That's just plain old x. Okay, so what's that going to be, Eric? Substitute in, what do you get? 0. So what you've now proven is that the absolute value, all the limits exist for the absolute value. Because on the right side, okay, guys? On the right side, it's just x, which is a polynomial. We already have that theorem. This is a proof. That's what you do in math. I want you to be aware of that. That's what you do in math in college, proofs. And then this is the left side. And now I showed that they were the same. So guess what? Absolute value can go in my list of functions where limits exist everywhere. What about the next one, though? Brad, you remember this one? We did this one several times. I'm going to write this as a piecewise function. Now, the problem with absolute value, it's got some crazy things. I've got a corner here, and you remember what happens at those corners? It's not differentiable. But the limits exist, it's continuous. When I mix it up with something else, then we got another problem. So let's as x approaches 0, sorry, Grant kind of messed me up here. As x is bigger than 0, what happens at 0, by the way? No, it's 0 over 0. We don't know. It doesn't exist. There's no value. Okay, Nick, put that away, please. Yeah. So from the right, it's x over x, which is 1. Okay? If it's from the left, it's x is still x, but this can be replaced with minus x. So that's what? And since the limit, and on the exam, you could write this. The limit from the left, as long as you're clear, does not equal the limit from the right. Okay, Eric, question? And what about at 0? If you put in 0, the value of the function doesn't even exist. So there's a hole in the graph. So Eric, what does this look like? If I wanted to graph this, that's right. Not everybody's remembering it, I don't think. As I look around, I see some people are not sure. It looks like this on the right and this on the left. It's a huge jump there. Limit does not exist. Okay. You know that the limit problems in this book are not going to be easy. This is the book they use at the University of Minnesota. Okay, they may be a different edition, but that's pretty much what they use. Now the squeeze theorem. Another word for this, depending on what book you look at, is the sandwich theorem, just to make you hungry. Hmm? Okay, this is not hard. Applying it's hard. But the theorem itself is not hard. Okay, guys. If the limit of G, that's this one right here, as we approach C, is equal to some L value, that's what this is, and then I have the limit of H, that's this one, and it also approaches L, so they both have the same limit, and F is sandwiched in between. That's why they call it the sandwich theorem. I don't even care. It could have even dropped out like this. Who cares? All we're looking at is the neighborhood of C. But I know that F is between G and H at that value. Well, then what's the value of F going to be? How? Sometimes you can find the value of G and H easily, and you know that F is between them, but you can't find that limit easily. Like this. No, this is 2, 3. And you may have questions, you may not, I don't know. Okay, that's a picture in the other book that you used last year. Okay, guys? Yeah, you need to pay attention. You're not going to know how to do this. Okay? This is a picture of x squared times the sine of 1 over x. If you try to take the limit right now, you would put in 0, right? The limit as x approaches 0 of x squared times the sine of 1 over x. I would get 0 times the sine of 1 over 0. Do you remember what happened to 1 over 0? Too many wiggles. I can bring it up and show it to you if you want. Do you want to see that one? Yeah. Now, I have my Inspire calculator, so I'm going to use that one. So I'm just going to add a page to what I've already got. Oh, I do this all the time. Hang on. I got to be there. You haven't done this for a while. This is the CX cast, and we're going to add a graph, and I'm in F2 because F1's already defined. Now, on this one, you find the trig right here. You could type it. Then I'm going to put in 1, and I'm going to put in x, and I want it to look pretty. No. Okay, you guys, there's the sine of 1 over x. Now, what's cool about the Inspire calculator is I want to zoom in on that, and this is so much easier to zoom on. I'm going to zoom in, and I'm going to do this. What value is it going to? We're at 0. I keep zooming in. It's got to go to a single value. It's wiggling like mad, if you think about it.
How far can we go until there's no more wiggles?
Until it gets solid.
Oh my gosh.
Now, you can't do this with an 84. Isn't that cool?
Keep going. Keep going.
After a while, the computer will fall apart.
No, just make it. Let's see if it falls. Let's see if it falls apart. Let's see it happen.
It might.
Keep
This one does a lot.
going.
Too many wiggles. You can do it in a second. Okay. But I want to get through this because you're not going to know how to do this. Okay, I'm going to move that out of the way. Okay. I'm going to use the squeeze theorem. And this is a BC topic, and yes, you have to know it. And what I want to do is find two functions, one smaller than this and one bigger than that it's trapped between. Okay, here's how I do this. Okay, Zach? I'm going to start with the one that's the problem. That's this guy. Whoops. That's the sine of 1 over x. So I take the sine of 1 over x, and I don't really know, but I do know it's trapped between two numbers. What is that always? What's the biggest value this is ever going to be? 1 and negative 1. Is that okay? So I take the one that's the problem, and then I want to make it look like x squared times the sine of 1 over x. So guess what I'm going to multiply by? X squared. As long as I have a valid inequality, I may multiply by x squared. Why does it have to be? It's squared there, but even if it's x, it also works. But I can't multiply by x because x could be negative, and then I have to reverse all those inequality symbols. So they were kind. And let's simplify that. Clean it up a little bit. So I get minus x squared is less than or equal to, I'm going to leave myself a little space here, x squared, Grant, times 1 over x, sine of 1 over x. And then this is x squared here. And now I'm going to take the limit. But what value do you think I want to take the limit? Yeah, let's take the limit as x approaches 0. If I can get the same value on the left side as I do on the right side, this is sandwiched or trapped in between, being squeezed, squeeze theorem, as x approaches 0. What's that limit? That's 0. I know that. And then I have this limit, which I don't know. That's the question. And you probably don't have a lot of practice problems on it. And then what's this one? As x approaches 0 of negative x squared? 0. Since this limit is 0, and this limit is 0, and we know that this is in between by the squeeze theorem, you have to give me this theorem. You can call it the sandwich theorem, I don't care. Theorem. And the limit, what do you think that limit's going to be? It's going to be 0. But you can't just take x squared times the sine of 1 over x, because this is wiggling. This guy's wiggling too many times. And even though, and this is 0, 0 times a wiggle doesn't mean anything. I don't know if it's 0. In this case, it is. Is x, limit of x, sine of 1 over x, is that x strong enough to overpower the wiggles? Maybe or maybe not. This is x squared. This is 0, and this is wiggling. Okay, guys? 0 times infinity, I don't know. We'll eventually get to all the forms. There'll be 7 of them. Okay? So when you do this, when you have to do these limits, and it's going to be in your book, Alex. Okay, shh. Guys, I'll be done in 2 seconds if you're quiet. Grant. You look for the function that's causing the problem. And then I've tried it, and usually it's a sine or cosine. I trap it between 1 and negative 1, and then manipulate that inequality to look like this. Okay.